Hello, my name is Greg Armstrong, and welcome to the tutorial on synchronized clocks. Today we'll be looking at phase lock loops and how they fit into clock synchronization. I will be covering the core building blocks of a PLL, how a PLL responds to injected noise, and then go over some applications for using PLLs. Before we jump into what are phase lock loops, let's talk about what is synchronization. So synchronization can be looked at as three different ways. One is not synchronized, which effectively just describes two completely independent clocks that are running at maybe some nominal frequency in relationship to each other, but there's some error in between them, like X parts per million or Y parts per million. Now, if we were to feed these two clocks into a counter and sample those counters over time, we would see that they would really have no relationship to each other than, yes, they're approximately incrementing 125 million times a second, but they would be incrementing at different paces over time, which means they'd effectively be drifting in relationship to one another. But what if we were to introduce some component along that path to allow us to share the same clock source between the counters? Well, this is where a phase lock loop fits in, and we'll talk about that in later slides. In this case, a clock is now feeding the same clock with the same error into a counter, and another counter would have the same clock and error represented at its output, so that now that if you sampled those two counters at any point in time, although they may not have the exact same value, they definitely would have the same static offset relationship between them. In other words, they would be incrementing at relatively the same pace. But what if we wanted to actually have the counters themselves be synchronized? Well, in this case, we need some mechanism to actually clear or load these counters with a value at approximately the same time. In this case, now if you sample these counters at any point in time, not only will they be incrementing at the same pace because of the usage of a phase lock loop, but they now actually would even represent the same value because of some other mechanism that has loaded their counters with the same value, such that when they get sampled, they should contain the same value at that point in time. The next few slides will talk about a phase lock loop, what it does, and some of its core building blocks. A phase lock loop generates a clock that is both phase and frequency locked to its input. The output frequency can be the same frequency, an integer multiple, or a fractional multiple of the input clock frequency. If you looked at the ratio of the frequency, it must be a positive integer or fractional number. But it means that you have lots of flexibility on the type of clocks you can generate and have some relationship back to the input clock. So let's look at some of the building blocks. The first one is the phase comparator. The phase comparator establishes an error between the input reference and the clock output. And it does this by using a feedback mechanism, which we'll talk about later. Most digital phase lock loop implementations use a time to digital converter, or TDC, as its phase frequency detector. And this will measure the phase of the two clocks and produce a digital word that represents the error. A TDC can be looked at as a time stamper, whose resolution is determined by its sampling clock, and generally in resolutions of picoseconds. The TDC will timestamp the reference and feedback edges, allowing the PFD to mathematically track the phase offset between the selected reference and the feedback clock. One thing to note is the measured phase difference can go well beyond a period or unit interval of the clock. Thus, the phase comparator must be able to measure over a very large range of multiples of input and output clock periods. An example is telecom defines a jitter and wander tolerance requirement of up to 18 microseconds peak to peak. If we were to translate this into a 125 megahertz clock with an 8 nanosecond period, the jitter tolerance requirement would equate to plus minus 1125 UE of that input reference clock. The phase error is then processed by the loop filter, or low pass filter, which will filter out any high frequency phase noise from the input reference. The loop filter is a combination of a proportional path and an integral path, both which will combine to generate a control signal to control the local oscillator. The loop filter determines the bandwidth of the PLL, or its cutoff frequency. What this means is any noise that is above the cutoff frequency will be attenuated or filtered, and anything below that will pass through. Sometimes you will hear this referred to as the passband. However, other functionality may actually be implemented into loop filter, such as phase slope limiting, locking range, and holdover functionality, which we'll talk about later. The loop filter control signal then goes to a voltage-controlled oscillator circuit, which will speed up or slow down the output clock. Again, most digital phase lock loops replace the voltage-controlled oscillator by a digitally or numerically controlled oscillator. A DCO consists of a free-running oscillator, which is typically sourced from a crystal or a MEMS, and it uses a digital synthesizer, which will pull the frequency either up or down using the digital word that represents the fractional frequency offset that's coming from the loop filter. And as mentioned earlier, the resulting output is then fed back to the phase comparator, and a lot of times along that path there will be an integer or fractional feedback divider to allow for the synthesizing of any frequency at the output. A common question I get is, can a phase lock loop be used with packet clocks? And the simple answer is yes. If we look at timing protocols such as 1588, we can really look at them as being a phase or time comparator as an input into the phase lock loop. Thus, it still follows the same model as a phase lock loop. The difference is because it's a timing protocol that is going over a network, you may have to introduce an additional selection block to maybe filter out outliers of packets or event packets that are coming over the network. Without some sort of packet selection, the variation of some of the delays of these event packets going through the network can have a significant impact to the performance of the loop filter. The loop filter would typically be designed to support a much lower update interval of the phase detector. Before we were talking about like a 125 megahertz clock going into the loop filter. So that's 125 million updates per second of the phase relationship of the input reference to the output. But with timing protocols, a lot of times they're running at much slower intervals, such as 1 packet per second or even 16 packets per second. And then if you take into account that some of the packet selection may actually filter out packets even before it goes into the loop filter, these could be even much lower update rates going into it. Because of this, typically packet-based phase lock loops require much more stable local oscillators, like an oven compensated or OCXO, or maybe some sort of assistance from the physical layer to stabilize the clock during the packet selection and filtering. So how do we know how the PLL is behaving once it has locked to a reference? Well, to know this, we have to look at some of the operating modes of a phase lock loop. A PLL has 3 core modes of operation: free run, locked, and holdover. Free run, much like the name implies, means the PLL is not tracking any reference clock and is effectively just running at the nominal frequency of the local oscillator. So if you look at the diagram at the bottom, you could look at it as the switch is open between the loop filter and the VCO. But once the PLL is starting to track an input reference, which means the phase detector is feeding the offset into the loop filter, the output clock can now track the input reference. Thus, the switch is closed, and we call this as being locked to the phase and frequency of the input clock. You may also hear this referred to as just normal mode. But what happens if the input clock fails or goes away? Well, in this case, the PLL is again no longer tracking its input. However, in this case, instead of just opening up the switch and falling directly back to the free running oscillator, a lot of times we can use information that we have stored or memory of when we are tracking the input reference in terms of what its last frequency offset may have been in relationship to the input reference. This allows us to effectively uh, create an autonomous synchronous source, but it's running at an initial frequency offset of the original input reference. One thing to note though is either in free running mode or the entry into holdover, when we look at the frequency, it's always going to be subjected to aging, drift, and the influence of temperature on the local oscillator. And you heard a lot about this in other tutorials talking about crystal oscillators and MEMS oscillators. The reason it's important to look at the local oscillator impact is when we have to go into holdover, a lot of times the oscillator is providing the constant frequency or drift rate while we are no longer tracking the input reference. A lot of times the frequency drift rate is represented as a linear component, such as a parts per billion or parts per trillion error over time. And a lot of times they'll define this not only in constant temperature, but even over variable temperature. However, if we look at the time or phase error component, this offset of frequency actually becomes an accelerator of the time error. And because of this, over time, you could actually drift quite far from the original time that you're at when you're tracking the input reference. This becomes important when you're trying to define things like time holdover or phase error holdover. Now that we looked at some of the core components and also some of the behavior or static behavior of the clock, let's now look at what happens when there is injected noise on a phase lock loop. Before we start talking about the PLL's response to injected noise, let's do a bit of a refresher on what is jitter and wander. So jitter is high frequency noises, generally defined as greater than or equal to 10 Hertz, whereas wander is low frequency noises, generally below 10 Hertz. You can essentially look at jitter as very short-term or variations of the clock, and wander is very long-term variations. So looking at the plot on the right would be the response of a PLL looking at the input in red, which has a lot of noise or jitter or short-term variations, to the output, which is blue, which effectively is tracking the wander or tracking the clock source. A lot of standard bodies will define what sort of tolerance a phase lock loop or a synchronous node must have when looking at noise. So as shown here, the blue would be your tolerance mask to say you must tolerate that level of noise coming into at the input reference, and the green represents the response of the PLL. So as expected, anything below 1 Hertz effectively should track the blue mask exactly, but anything between 1 and 10 Hertz, because of the filtering definition of a synchronous Ethernet clock, you should start seeing the attenuation of that clock in that range. And once you go beyond 10 Hertz, you should see full attenuation of any noise of that clock. So in summary, a function of a PLL is to attenuate jitter and to transfer wander, and do this while tolerating the noise at the input without losing lock to the reference input. This slide is showing some of the step response and jitter transfer of a type 2 PLL. A PLL step response will have some sort of overshoot, and the frequency domain will have a peaking around the cutoff frequency. The phase corrections are generally done through the proportional path of a phase lock loop filter, along with any other phase limiting. Whereas frequency or drift corrections will be done through the integrator path, including some sort of damping to minimize the gain peaking near the cutoff frequency. Now let's look at the response of a PLL output when it comes to an injected noise. There are two primary sources of noise, the input itself and the local oscillator. Without a loop filter, any garbage in will effectively be garbage out, and this includes jitter, wander, and phase noise. The job of a PLL is to attenuate jitter And for a network synchronization PLL, it's also to attenuate certain wander. The resulting clock must meet phase noise per a typical target physical layer clock, which is like an Ethernet SerDes or an RF clock. The local oscillator attributes some of that noise as well, but it effectively acts as a high-pass filter onto the output clock. So this means any high frequency noises coming from the local oscillator will immediately pass through onto the output. So now that we understand some of the characteristics of a PLL, let's look at some of the applications we can do with PLLs and take advantage of some of these known characteristics, such as low pass and high pass filtering. A very common application we're seeing today is the combining of two clocks into a single clock. We see this at the ITU-T in the definition of its telecom boundary clock, using physical layer assistance in generating the packet clock. And we also see this even at GNSS receivers, combining a local very stable clock with information coming from GNSS representing UTC time. Well, how could we maybe do this type of combining using phase lock loops? Well, the key thing is to remember some of the transfer characteristics of a phase lock loop, where any noise coming in from the input is attenuated or has a low pass filter characteristic, but any noise coming from the local oscillator will have a high pass characteristic of the noise to the output. Well, what if we actually took the output of one clock and inputted it into the oscillator circuit of another clock? If we now look at the characteristic of the PLL's output at the bottom, you can see that we created effectively a band pass filter for the noise coming in from the upper clock to how the noise is represented at the output clock. And the noise coming from the bottom input reference still passes through with a low pass filter characteristic coming out of the output. In addition to looking at the filtering characteristics, an interesting aspect is the spectral densities or the phase noise that you can create by doing this type of technique of clock combining. If we took two input references, we can effectively not only combine the noise characteristics of the two inputs into the output, but even the phase spectral densities of the two inputs can be represented at the output. So effectively, you could take advantage of certain characteristics of each clock in terms of its short, medium, or long-term stability in order to generate your final clock output. There are already many examples of doing clock combining in order to get much more stable clocks coming out of the outputs. Below are a few applications. One is like an enhanced primary reference time clock, which was introduced in some of the tutorials and you'll hear more about at the conferences. Here you're combining the characteristics of the GNSS receivers, which contain time, along with maybe local clocks like a cesium clock, which contain frequency, and combining them to represent a single clock at the output. But we're even seeing this in network synchronization. In telecom boundary clocks, the use of physical layer assistance is used to stabilize the packet clock and also use it for holdover characteristics on the loss of the packet clock. And here is an example of the telecom boundary clock where I just basically applied the two PLL architecture concept to demonstrate how it could implement the pass band filter characteristics of the synchy noise to PTP output. And again, this is all utilizing existing blocks of a phase lock loop, including even using a packet-based PLL to lock to the packet-based clock. I hope you found this tutorial useful and learned a lot more about phase lock loops and the usage of phase lock loops in existing systems. If you have any information, feel free to reach out to me at greg.armstrong.uw@renesas.com. Thank you.